Hello everyone, and thanks for watching Edupedia World videos. In this video, we solve the time-independent Schrodinger equation for one of the simplest cases possible, the infinite square well. So in the infinite square well, we have two walls which have potential infinity, v is equal to infinity, v is equal to infinity. Let's say this is x is equal to 0, x is equal to a, and at this point v is equal to 0. So the potential is infinite everywhere except between x is equal to 0 and x is equal to a. In between these 2 points, the potential is 0. In the classical case for classical mechanics, what would happen was, if there was an object kept between x is equal to 0 and x is equal to a, and it was given a velocity in either direction, it would just bounce back and forth forever between these two walls. But in the quantum mechanics case, it's slightly more different, and let's try to solve the time-independent Schrodinger equation for this case. So the infinite square well can be written as v of x is equal to 0 for x between 0 and a, and v of x is equal to infinity everywhere else. So we know that for a particle within this infinite square well, the probability of finding the particle outside x is equal to 0 or x is equal to a will be 0 because the potential is infinite. So the particle wave function will only be non-zero between x is equal to 0 and x is equal to a. So our goal is to try to find that out. So what is the time-independent Schrodinger equation? Minus h square by 2m d squared psi by dx squared. Notice that this is not a partial derivative because psi only depends on x now, because this is the time-independent version where we've removed the time dependence from the time-dependent case or the standard Schrodinger equation, plus v psi is equal to E psi, where E is the energy. Now, for x that is less than 0 or greater than a, we'll have psi is equal to 0. Because the probability of finding the particle outside these 2 points is 0 because the potential is infinity. So psi will be 0, psi of x is equal to 0 for x less than 0 or x greater than a. But between 0 and a, we need to find psi of x. So it will be something psi of x between 0x and a, between 0 and a. So in this case, v of x is equal to 0. We know that. Now we are solving for 0 less than equal to x less than equal to a, and we know that the potential is 0, so that we can simply remove this term. So this is our equation, and we can write this as d2 psi by dx squared is equal to minus k squared psi, where k is equal to root of 2me by h. Right. The reason we've written in this form is because we generally know the solution to an equation like this, and it is psi of x is equal to a sine kx plus b cos kx. Right, so anytime you have the derivative equal to minus k squared times psi, where k is this positive quantity, psi of x will be a sine kx plus b cos kx. So when you differentiate it, you'll get a k cos kx and minus k sine kx. You differentiate it again, you get minus k squared times a sine kx plus b cos kx. Now this is a wave function in which we have two unknowns, a and b, and we need to find the values of a and b, and that is done by using what are called the boundary conditions. These are similar to initial conditions whenever you have velocity and you're trying to find out position, except we know the values at the two boundaries, so it's called the boundary condition. Now what are the boundary conditions? And the boundary conditions, I'll not give you a proof for this, but the boundary conditions state that psi of x is continuous everywhere and d psi by dx is continuous everywhere, except there is an exception where v is equal to infinity. So that is true in this case of the infinite square well. but psi of x always has to be continuous. And d psi by dx will be continuous in most places, but it will not be continuous whenever the potential is infinity. So that means at x is equal to 0, psi of x has to be continuous. D psi by dx does not need to be continuous because on the left side the potential is infinity, on the right side the potential is 0. So these two are boundary conditions which we'll use generally in different cases. In this particular case, all we need to do is use the first boundary condition. We got psi of x to be a sin kx plus b cos kx, where k was root of 2me by h. So the first boundary condition tells us that psi is continuous everywhere, means it is continuous at x is equal to 0. But we know that just to the left of x is equal to 0, psi of x is 0. This is, by the way, only for 0 less than equal to x less than equal to a. Psi x is 0 everywhere else, right? So at this point it is 0, which means at this point it should be 0 as well. So that means psi of 0 should be 0. Similarly, to the right of x is equal to a, the potential is infinity, which means psi of x is 0. That means just at a, psi of x should be 0 as well, because it needs to be continuous. So psi of a is 0. So these are the two boundary conditions. The first one tells us that psi of 0, so a sine of 0 will be 0 plus b cos of 0. So this basically tells us that b is equal to 0, because psi of 0 would be a sine of 0, which is 0, plus b cos of 0, which is b, so b is equal to 0, which gives us psi of x as simply a sine kx. Now the other boundary condition tells us that psi of a is 0, which means that a sine of ka is equal to 0, which simply tells us that ka is equal to n pi, or k is equal to n pi by a, where n is an integer. So because we have certain discrete values of k, now this tells us that ka could either be pi, 2 pi, 4 pi, 6 pi, but it cannot be something like pi by 2, because in that case psi would not be 0 at x is equal to a. But what is k? That is root of 2me by h, and that is equal to n pi by a. From that we can calculate the value of energy. So 2me is equal to n squared pi squared h squared by a squared, and we get 2m here. So E is equal to n squared pi squared h squared by 2ma squared, where n is an integer. So that means, like we said in a previous video, we get certain values of allowed energies. So not every value of energy is allowed, only certain values. So in this case, the values would be E is equal to pi squared h squared by 2ma squared, 6 pi squared h squared by 2ma squared, and so on. But it can't be simply 3 pi squared h squared by 5ma squared or something like that. So these are the only allowed values of the energies. Now let's look at what the allowed values of energies represent. So we'll look in detail now at cases such as n is equal to 1, n is equal to 2, n is equal to 3, and so on. So let's look at the case where n is equal to 1. So here we have psi of x is equal to a sine pi a by x. So the graph looks something like this. At x is equal to 0, it's 0, and it's 0 at x is equal to a, because it will be sine of pi. And between them it is positive, so this is the way it looks. This is x is equal to 0, x is equal to a. Remember, mod psi squared is the probability density. So that will also have a curve something like this, which means that the probability of finding the particle at one of the two edges is 0. And the highest probability is of finding the particle at the midpoint at x is equal to a by 2. Another thing we can do is normalize it so that the integral of mod psi squared is 1, which means the integral, and we only need to integrate from 0 to a because everywhere else psi of x is 0, so the integral will be 0. A squared sine squared of pi a by x. Sorry, my mistake. This is pi x by a. Pi x by a dx. And this has to be equal to 1. And if you try to calculate the value of integral sine squared pi x by a, that will come out to be a by 2. So this tells us a squared into a by 2 is equal to 1. You can do the integral yourself, which means a is equal to root of 2 by a. So which finally gives us the normalized wave function root of 2 by a sine of pi x by a. This is what is called the normalized wave function. And the energy in this case would be pi squared h squared by 2ma squared. Let's look at the second case, n is equal to 2. In this case, psi of x will be a sine. Now we'll have 2 pi x by a, because now n is equal to 2. By the way, the previous one was called the first stationary state or the ground state. This is called the first excited state. The ground state is the one which has the lowest energy, that was n is equal to 1. Now n is equal to 2 will be the first excited state because it is the first state after the ground state. This terminology is very similar to Bohr model, in which you have the ground state of an atom, of an electron, the first excited state, second excited state, and so on. So in this case, what would the graph look like? This is 0, this is a. So at x is equal to 0, psi is 0. At x is equal to a, psi is 0. But psi is also 0 at x is equal to a by 2 at this point. So it would look something like this. Now notice that this has some peculiarity, which means the probability of finding the particle at the midpoint a by 2 is 0. Now this is completely different from the n is equal to 1 case. When n was equal to 1, we had the maximum probability of finding the particle at x is equal to a by 2 or the midpoint. But when the particle is in the first excited state when n is equal to 2, it has 0 probability of being found at the midpoint. It has the highest probability of being found at a by 4 and 3a by 4. Don't be worried about the fact that this is negative, because mod of psi squared is what really determines the probability density. So in this case, it would be 0 at 0, a by 2 and a, and it would be maximum at a by 4 and 3a by 4. Similar to sound waves and transverse waves on a string, this terminology here as well. The points where psi is equal to 0 are called nodes. So for n is equal to 1, the nodes would have been 0 and a. For n is equal to 2, the nodes are 0, a by 2 and a. And the points where psi is maximum, these are called the antinodes. Just like when you have a traveling wave on a string and it goes forward and comes back and makes stationary waves, you have nodes and antinodes. The energy in this case will be 4 pi squared h squared by 2ma squared. And the normalization will be the same, because we'll want integral 0 to a squared sine squared of 2 pi x by a dx is equal to 1. And that will once again give me a is equal to root of 2 by a. So from that we can get n is equal to 3, and further on, which is for a standard n, psi n of x, the normalization is the same for all of them. It will be root of 2 by a sine of n pi x by a, with the energy being equal to n squared pi squared h squared by 2ma squared. So this is it. We've pretty much solved the question of the infinite square well now. Now there are two properties of these wave functions that are important, and these properties will arise in a number of different questions we'll see. And that is that these wave functions, these stationary states, are orthogonal and complete. So what does orthogonality mean? It means that for any two numbers m and n which are not equal, integral of psi mx star. By the way, in this case, the wave functions are real, so the complex conjugate is the same thing, into psi nx dx is equal to 0 if m is not equal to n. So they are orthogonal, means that if you integrate the product of two of them, and this goes all over space, but because everywhere else it's 0, we only really need to do this between 0 and a. This is true, and if m is equal to n, then this becomes the orthogonality case, which means that integral of psi m star x into psi mx, if both of them are same, this has to be equal to 1. So these two can be combined into a simple definition: integral from 0 to a psi m star x into psi n of x dx is equal to delta mn, where delta mn is a symbol called the Kronecker delta, and its value is 0 if m is not equal to n, and is 1 if m is equal to n. Right, and we can prove this as well. This case comes directly from normalization. The fact that we put root 2 by a in front means that this is true for all functions, and let's try to prove this first one. So integral 0 to a psi m star multiplied by psi n. So that will give us 2 by a, because we have root 2 by a is sine m pi x by a sine n pi x by a dx. And this we can write as 1 by a, 2 sine a sine b is cos a minus b minus cos a plus b. So integral 0 to a cos m minus n pi x by a minus cos m plus n times pi x by a dx. And this just comes out to be 1 by m minus n times pi, and a will cancel with this a, sine of m minus n pi x by a, and then you have minus 1 by m plus n times pi sine of m plus n pi x by a, and the limits for both of them are from 0 to a. We are assuming that m is not equal to n. Now we can see that even though that is true, m and n are both integers. So m minus n is an integer and m plus n is an integer. And both these terms, when you have x is equal to 0, are equal to 0. And when x is equal to a, both the terms are integral multiples of pi. So we get this is equal to 0, which means that the wave functions are orthogonal. The second thing I stated was that the wave functions are also complete. And complete means that every function can be written, or every possible state can be written as a linear combination of psi and x, which are the stationary states. So remember, the stationary states are the ones in which the expectation value of quantities is constant and in which the energy always is the same value, that is m squared pi squared h squared by 2ma squared. But a particle does not need to be in either one of those states. It does not need to be in the state n is equal to 1 or n is equal to 2. It can in fact be in the state psi 1 of x plus psi 2 of x. Now a function, if a particle is in this state, that is psi 1 of x plus psi 2 of x, then it does not have a particular value of energy because there are two values of energy here. This could be pi square h squared by 2ma squared. This would be 4 pi square h squared by 2ma squared. So the net energy would be something between that, which means this is not a stationary state. But even though this is not a stationary state, this can be the actual state of the particle. There's no rule which says the particle has to be in one of the allowed states, right? It can be in a combination of them as well. And so completeness states that no matter what the function is, every single function or every single state that a particle might be in can be written as a linear combination of psi and x, which means that it can be written in some form as summation Cn psi n of x. Now, we'll not give the proof of this right now. It will come in a later video when we start doing linear algebra. But in this specific case, we can see that this is true because this basically becomes the Fourier series. So if you have any function f of x, that can be written as root of 2 by a summation n is equal to 1 to infinity Cn sine of n pi x by a for appropriate Cn. So every single function can be written in this form, and this is basically a theorem in the Fourier series which said that every single function which has this function will obviously have a value 0 at x is equal to 0 and 0 at x is equal to a. So will all these functions. So we already know from mathematics that Fourier series states that this function can be written in terms of its harmonics or sine n pi x by a. Now how do we get the value of Cn? That is quite important, and that is done by what is called Fourier's trick. Where what we do is to get Cn. So let me just first repeat what we've done here. We have already solved the equation and gotten all the stationary states which are psi n of x and gotten the energies for them. Now we are given state of the particle and it is not in any one of those stationary states. So we can represent it as a combination of the stationary states after finding the appropriate Cn. So right now, given f of x, our goal is to find Cn. And so what we do is we multiply both sides by sine of n pi x by a. So let's change the variable for a second and try to calculate Cm. So to calculate Cm, what we do is integral of psi m star times x f of x dx. So we multiply both sides by psi m star of x and then integrate from 0 to a is equal to root of 2 by a times summation n is equal to 1 to infinity the integral of Cn sine n pi x by a sine m pi x by a dx. But we just proved a few minutes ago that the stationary states are orthogonal, which means if m is not equal to n, then this integral is 0. So in the RHS, the integral is only non-zero when m is equal to n, which means what we get is, and obviously the integral of sine n pi x by a into sine n pi x by a will be root of a by 2, which will cancel with this. So ultimately what we get is Cn is equal to Cm rather, integral from 0 to a psi m star x into f of x dx. So this completes our solution of the infinite square well. Right. So we started off with the time independent Schrodinger equation minus h squared by 2m d squared psi by dx squared plus v psi is equal to e psi. This was the time independent Schrodinger equation, and then we had a potential v of x which is 0 for x between 0 and a and which is infinity otherwise. So everywhere that the potential was infinity, we knew that psi of x is 0, and in this region psi of x is non-zero. So we put v is equal to 0 here and we got the solution psi of x is equal to a sine kx plus b cos kx, where k was equal to root of 2me by h. And then we applied the boundary conditions that psi of x is 0 at both x is equal to 0 and x is equal to a. One gave me b is equal to 0, the other gave me ka is equal to n pi. So from that we get a sine of n pi x by a. And then we normalized it to get the value of a, which was root of 2 by small a. And the fact that k was equal to n pi by x, because kx was equal to n pi, this told us, n pi by a, this told us the energy was equal to n squared pi squared h squared by 2m a squared n. So we got some allowed energies, which itself is completely different from the classical case. In classical mechanics, if you have a ball kept between two walls which have infinite potential, the ball could have any energy and it would just move back and forth between the two walls. But in the quantum mechanical case, the particle can just not have any energy, it needs to have specific energies which are of this form, n squared pi squared h squared by 2ma squared. And the wave function in that case would be root 2 by a sine of n pi x by a. This gave us the ground state, n is equal to 1, and the excited states, n is equal to 2, 3, 4, and so on. Finally, if we are given what the state of the function is, we can represent it as a linear combination of these states. Remember, these states are stationary states where the expectation values are constant. That does not mean every state has to belong to one of these categories. It can be a linear combination. For example, 2 psi 1 of x plus 3 psi 3 of x plus 5 psi 7 of x. Of course, we would need to normalize it. This is normalized, but it can be something of the form of this, where the energy would be a combination of these three energies. So in that case, what we did was use Fourier's trick and try to find out the coefficient Cn such that every single function initial psi of x can be written in the form of the linear combination summation n is equal to 1 to infinity Cn psi n of x. And once we found Cn, our problem is solved. We have represented the initial state in terms of the values of Cn, and then we can find out anything we need to find out, such as what is the energy and so on. In the next video, we start a new question which is slightly more complicated than this, which will be the harmonic oscillator. Thank you.